Well, it's so weird. It has everything in there backwards. Oh well. So with combustion, remember combustion is when you have an increase in the number of bonds to oxygen. So here you only have the oxygen bonded to each other. After the reaction, you have 2 bonds going to oxygen from carbon. You have 2 bonds going to oxygen from the hydrogen. And the combustion reaction has the production of carbon dioxide and water. Now, a problem with this reaction is the buildup of greenhouse gases in our atmosphere. And there is strong evidence to suggest that the human burning of fossil fuels is resulting in global warming. It is a controversial subject, but most scientists agree that global warming is occurring. Some scientists will say that we are just on a normal upswing from the last ice age, and these are normal fluctuations, but most scientists believe that we're warming at a much more alarming rate. And the concentrations of carbon dioxide in our atmosphere are higher than they have ever been. This is one reaction that occurs pretty spontaneously. All you need to do is provide that activation energy, a spark, so to speak, and the reaction will take place. They are generally limited in reactivity, and other reactions that occur will often need a catalyst or high temperature and pressure conditions. So a halogenation reaction is where we are taking a chlorine or a bromine or a fluorine, usually it says chlorine or bromine, and we're having it take the place of one of those hydrogens. So here you can see the chlorine is added on there, which reminds me of one of the questions in the post-question ones. Brittany, that was you that texted me, and it said to draw as many possible isomers as you can with C4H6. Was it CL1 or CL2? CL1. Okay. So we're going to have 4 carbons in a row. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Was it C4 or was it C2?
It was 4.
Do you guys know? It's not. I feel like I did this last year and I'm not remembering.
C4H6Cl.
C4H6Cl. Well, what if we put a double bond there and a double bond there? 1, 2. 1, 2, 3, 4, 1. There would be no hydrogen there. There could be one there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4. Oh, we still have some place to put our. Still need some place to put our chlorine. 1, 2, 3, 4, 5, 6. This carbon has 4 things around it. We could stick a chlorine right there. This carbon has 1, 2, 3, 4. This carbon does not. I don't know what to do with it, honestly. Well, you guys are building models today. I'll play around with it. And I feel like it might be a typo, but I'll Google it. And I'm sorry I'm not prepared to answer that question as good as I could be. I might ask you to tell me how many isomers you could make with this. And there would really only be two possibilities, because we could put the chlorine in the middle, right? Or we could put the chlorine on either end, which would be the same thing. So this would be one possibility. And this would be one possibility. Now this isn't any different than if I would have put this here, or here, or here. It's still a chlorine attached to an end carbon. If I would have put it here, it would be like switching the molecule around. If I would have put it here, it would be the same as putting it right in the middle. So we have two possible isomers with this compound, and that's putting the chlorine either in the middle or one on the end. I won't ask you very hard isomer questions, and I hope that they'll be pretty straightforward. But I will work on that one while you guys are building models today. So with this halogenation, again, that it's a substitution reaction. The chlorine is substituting with the hydrogens. Dehydrogenation is occurring where you have hydrogens being taken off of this molecule, and here you have fewer hydrogens. So turning an alkane into an alkene. This is just cracking. You are breaking this up into smaller bits, and the isomerization is just rearranging things. Okay, so this is an example. It says the chlorination of methane with excess chlorine can produce each of the compounds shown. So we can start with regular old methane and then add chlorine. So one chlorine is being added here. It's taking the place of one hydrogen, which is called dichloromethane. Here we're adding, or this is chloromethane, methane, chloromethane, dichloromethane. We have two chlorines. Here we have three chlorines, trichloromethane, and then eventually getting tetra carbon tetrachloride, one carbon and four chlorines. So if they're going for an end product, or if they're going for any of these products, they would just need to stop wherever, they would need to stop that reaction wherever they wanted that product to be formed. So when we have a halogen, like fluorine, chlorine, bromine, or iodine, attached to a an alkane, it's called an alkyl halide. So it's referred to, so this is referred to as the alkyl halide, and the way that we name it is to take the root, the chlorine becomes chloro. So because this chlorine is attached to the second carbon, this becomes 2 chloro, 1, 2, 3, 4 butane. Here we have a chlorine attached to this carbon, and we want our numbers to be as small as they possibly can. So if you look on this one, the longest chain is 1, 2, 3, 4, 5, and we have a chlorine attached here, and we have a methyl group attached here. Remember, the root methyl refers to one carbon. If it's a methyl group that's attached, it's a CH3. So when we number, if we number from this direction, it will give us the lowest possible numbers. As opposed to numbering in this direction, it would be 1, 2, 3, 4 chloro, 3 methyl pentane, and those are lower numbers. So do you guys remember why we say 2 chloro, before methyl? Right, it's alphabetical. Even if we had 2 methyl groups, well, I guess C would, I was thinking dimethyl, the C would come before that, but, so it's alphabetical. Here, we have a bromo group, a chloro group. So 2 bromo, bromo comes before chloro, 2 bromo, 1 chloropane, propane, 1, 2, 3. And here, 1, 2, 3 propane, and we have 2 chlorines attached to an end carbon, which makes it 1, 1 dichloropropane. So that's how we treat those groups. All right, so alkanes are produced from natural gas and petroleum. And that comes from the decay of plants and animals. Most petroleum formed in a warm, shallow sea. Now, 240 some million years ago, Wisconsin was covered by a warm, shallow sea. Did you know that? All of the rock along the Niagara Escarpment, High Falls State Park, all of Door County is all limestone. And limestone is coral reef environment. That limestone goes all the way down to Milwaukee. Some of it has lots of fossils in it, but the Wisconsin warm shallow sea was a very prime condition for petroleum to form 245 million years ago, which is when most of the petroleum formed. The only way that petroleum can form and get trapped, or actually get concentrated in an area, is if it gets trapped in some sort of structure. So if you have all these organisms, they die, they get compressed, eventually petroleum forms, and what happens is that petroleum is less dense than the rocks around it. It just starts coming up, and it might hit like a resistant rock layer, and it might travel along that resistant rock layer until it gets cracks, and it eventually makes its way to the surface. So where geologists find petroleum, and I'm just sharing my geology stuff here because it's really cool, is in areas like this where rocks have been kind of folded, and you have like a resistant rock layer, like a slate, or a really a rock that doesn't crack very easily. That petroleum can rise up and then just get trapped in that structure. And this is what, those are the structures that we're tapping into when we're drilling for petroleum. So there probably was a lot of petroleum that formed in Wisconsin. The problem with Wisconsin is under Lake Michigan, the rocks are kind of tipped this way. So let's say this is Door County with all of the rock escarpments in Door County. This is called the Niagara Dolomite, which is a form of limestone. These rock layers go underneath Lake Michigan and come up here at Niagara Falls. Isn't that cool? That's so cool. The same rocks that are in Door County travel under Lake Michigan and come out again over at Niagara Falls. Now, if we did have any oil forming in this, it would have been long gone. It would have come up, and even if there was a resistant layer in there, it would have just traveled all the way up and made it to the Earth's surface. So they have found pools of it in the Lake Michigan basin, but there's been legislation that says we can't tap into, we can't do any sort of oil exploration within the Great Lakes region to protect the lakes. So gasoline is a mixture of hydrocarbons. You can see that these are aligned structures. So this one is a 1, 2, 3, 4, 5, 6, 7, 8 carbon structure with 2 methyl groups. Here we have a cyclical structure So this would be called 1, 2, 3. So there's 6. So the name of this would be 1, 2 dimethyl, because each of this is a carbon group, remember, and each carbon is going to have 3 hydrogens. So 1, 2 dimethyl cyclohexane. Cyclo because it's cyclical. Did we talk about cyclostructures yet? I feel like maybe we haven't. Maybe we did, maybe we didn't. If we didn't, we're going to talk about it yet. And if we did, then we're just reviewing right now. I'm teaching this stuff in my advanced chem class right now, so there's overlap and I might get confused. So 2 methyl groups. Now we call it 1, 2 because you want to start numbering again where the lowest is. We do 1, 2, 3, 4, 5, 6. So we would just pick one of these to be 1. We're going to take that to be 2 because it'll give us the lowest numbers. This one right here is just for practice. We have a cyclopentane because there are 6 carbons. Carbon, 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 carbon. And I'm going to choose that to be my 1. I'm going to choose this to be my 3. That's a carbon and a carbon. So we have an ethyl group here and an ethyl group there. So 1, 3 diethyl cyclopentane. So what they do with the octane rating that you see on your gas tank, the 87, 89, 91, the octane rating is just a ratio of what they're calling isooctane. I don't know which one of these is isooctane off of the top of my head, and heptane mixture. It's just a ratio of different compounds in the engine or in the fuel. The higher octane fuels result in less engine knocking, but that, you know, back in the old days they would always say use 91 in your car and you won't get engine knocking, but a lot of our cars nowadays are made to, like my car says put 87 in it because that's what it's designed for, and it's not running. So you know, each of our cars I think run better on certain blends, and sometimes it's 87 and sometimes it's 91. So we can put additives in our gasoline to boost the octane rating. They used to use tetraethyl lead, and we don't use it anymore because we know that lead is really bad for you. If you are, if you're ever thinking about buying property, and you guys are all young, you're going to end up in that stage of your lives, do some background history on where you're purchasing and find out if there has ever been any buried gas tanks on the property, because a lot of farms used to have buried gas tanks. Like a lot of them still do. They have gas on their farm to fill up their tractors and stuff like that, whether it's diesel or gasoline. If you are going to buy property, find out the history and find out if there's been any, because a lot of those old tanks had the leaded gas in it and have leaked, and that lead could get into your water system, and especially if you're out in the country, that's the groundwater that's going to your wells. So it's really important to get soil samples done prior to even making an offer. Or you can make an offer on a home and have some contingencies, like we will buy this upon the contingency that a soil sample is done and it comes back clear, a water sample is done and it comes back clear, and that there is no evidence of any old gas tanks being buried on the property. So those are things to think about that you might not have ever thought about before. But where gas tanks used to be with this leaded gas in there. It's bad news. It's really bad. Oh, we didn't talk about the cyclo ones. So they put the ethanol in there now because it's more environmentally friendly, and the ethanol does increase that octane rating. So here they are. The cycloalkanes are similar to alkanes. We do the same thing we did before. Prop is the prefix for 3. 1, 2, 3. Cyclopropane, cyclobutane, cyclopentane, and cyclohexane. Now, cyclopropane and cyclobutane tend to be more reactive. And the reason is to have 3 carbons or 4 carbons in a circle like this is really not very stable. So it's not as rigid, it's not as stable as these these are like more solid structures. So they're so close together, any movement of the molecules stresses and strains these bonds. And if these bonds get stressed and easily strained, they're going to have a tendency to be more reactive compared to these structures, which tend to show more stability. So more reactive because they're not quite as stable. So this just summarizes that they have the higher reactivity, these bonds get strained. These smaller bond angles result in a more strained, confined molecular arrangement. Cyclohexane, there is 2 ways that cyclohexane can be built. One is called a chair conformation, and if you build it and were able to to put the molecule up, you would have like one part of the molecule kind of tipped up like this, one sitting flat, and one going down. So that would be like looking at a side view, and that's kind of what this is supposed to indicate. The other is where both of them are tipped up like that. And these conformations aren't really that important with the cycloalkanes, but they do become more important when we're talking about sugars. Sugar molecules are 6-sided structures, and glucose molecules can have the same sorts of conformations, and depending on how they're oriented, changes their properties a little bit. So here it says, draw the structure for 2 cycloalkanes that have a molecular formula of C4H8. We can have one like this, where we have C4 like that, and each of these carbons has 2 hydrogens. Or we could make a triangle of cyclopropane with a carbon there. And let's see if this gives us our 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. So this carbon has the 4 things attached to it. So those are the 2 ways that you could draw cycloalkanes with 4 carbons. And this could be drawn like this if we're just doing the aligned structure. It is implied that each of those corners is carbon, and this could be drawn, that's really bad, like that. Showing that we have a cyclopropane with a methyl group sticking off of it. So we would call this cyclobutane, and we would call this methyl cyclohexane. propane. And those are the same two pictures that are on here. So, I'm just going to get through this slide presentation and then we'll take a break. When we're naming them, we have to name the however many carbons there are in the ring structure, and we call that the parent cycloalkane. And then this is called a substituent group. This is a methyl group, so this would be methyl cyclohexane. Now, there's only one methyl, so we don't have to say, okay, this is on the number one carbon, because it's just assumed that wherever it's attached to is going to be wherever it's attached to. The only time we would need to number these is if there's more than one group attached, which is probably in the next slides. So with polysubstituted, that means more than one thing attached. We're going to number the ring either clockwise or counterclockwise. It depends on, again, which direction is going to give us the lowest numbers. Is that a dog barking? Oh. I won't tell them that I said that. So here we have two methyl groups, 1,1-dimethyl, 1,2-dimethyl, 1,3-dimethyl. Since, well, these are right across from each other, it's 1,4. Now all of a sudden you see it seems like it's wrapping right around, right? Like this is going, but in order to give us the low numbers, now we're going to have to start numbering from this side, and that becomes 1, 3. So this and this are exactly the same molecules. It's just that they're flipped of each other. And these two are exactly the same molecules. And this one and this one happen to be exactly the same molecules too. So we have writing structural formulas for 1-bromo 2-methylcyclopentane and 1,1-dichloro 3-ethyl cyclohexane. I am going to leave that on there as my last slide, and then I will let you guys attempt to draw them without looking at your PowerPoints if you have them, and then we'll come back to the answers after our break.